Okay, today will be the option. That means we try to introduction to you on the radio frequency. If you want to be a technician, you better get a knowledge about the IF, especially for the people working in the defense company. Okay? And you have to take the note and also try to read it under time in order to maybe understand it. Okay? So the first thing you can say that they just list the different frequency from what frequency to what frequency. Okay? They can be from 30 hertz to 300 hertz and so on. And if you're looking into here, you can get a wavelength. That means the distance of the signal transmitted over the air. Okay? And the other thing you can see, this is the frequency. So frequency going up and the wavelength going from right to the left. Low frequency, the wavelength will be longer. Okay? Just for your document. Let's see. You see one window or two windows?
Two.
Two. So that means I have to make sure I can do a right thing.
One.
Okay, so I have to reshare changing the display. Now you see only one, right?
Yes.
Okay, that's good. Okay, so they just telling you frequency, what is a high frequency or very high frequency, ultra high. Okay, so basically just for your document. And same thing. Cycle. One complete occurrence of a repeating wave, such as one positive, one negative alternation of a sine wave. And what is the frequency? The number of cycles of a signal that occur in 1 second. Very, very important to you to get a basic definition. Period. The time distance between two similar points on a periodic wave. Wavelength. The distance traveled by electromagnetic radio waves during one period. That's what you already know. That's what for the filter. Okay? They're talking about the narrow band, okay, and try to improve the selectivity. So you can see you can get a one filter section 2, 3, 4. So the best for now, you can see they will be 4, right? That will be a narrow band. What they mean when they say one filter section?
Is that one pole?
Exactly. One pole. 2 will be 2 pole. 3 will be 3 and 4 will be 4. Okay? One pole, that only telling you on the circuitry filter they get only one R, one C. And 2 will be 2R, 2C, and so on. Okay? So why we can say the 4 selection will be much better on the first one, for example. Compared to the first one and the 4 section. You say the 4 will be much better. Question is why?
Bandwidth is narrower.
It has a much steeper attenuation rate of unwanted signal.
Basically, that's just telling you one thing. They will be uh, reduce the noise.
It has a steeper roll-off rate.
Yeah, the thing in narrow band, you get less noise than while, you know, the big one. Okay, that's what we already done.
Is that
Now,
also to apply to capacitors? Impedance is lower.
now that depending on what kind of the filter. We not go into the detail. You select a capacitor or resistor or inductor. Okay? And on that one we already get through also. They given to you different filter from different engineer. Okay? They design. If you're looking on uh, Chapter electrical butterworth or best sell, which one do you think is the best?
The best cell.
Which one?
That's
The
what
best cell.
Best sell?
Yes.
Okay, now you say the best sell will be the better filter in this display here. But why? Can you tell me why?
Because within the pass band, it has the least amount of ripple, and it has the steepest roll-off rate when you're getting your unwanted signal.
Perfect. That's the thing. If you're looking on that, the good filter will be the cutoff very sharp. Okay, and also they have to not get much ripple. What that mean for ripple?
Noise.
Exactly, just the noise. Okay, if you're looking into the one very good cutoff, that means temperature right here. Very good cutoff, however, they get a lot of noisy. Okay, so for this one, if they asking you, then the good choice will be bad cell. Okay, the thing is they will be a flat. Okay, during the mid range, and also the cutoff still be good. Okay, now, this brings it up another thing. They're talking about sideway. You already know sideway. Basically, they just bring to you a up here. You get a sideway, they get a fundamental, and also they can get different, okay, third harmonic, fifth harmonic. What that mean? I given you example. If you get a 1 kilohertz sideway, so the third harmonic will be what frequency?
Which one?
3K.
3 kilohertz. Okay? I'm not talking about second. We're not using second. Okay? Third harmonic mean 3 kilohertz. Fifth harmonic 5 kilohertz. Seventh harmonic will be 7 kilohertz. Okay? And now, if you're looking on this thing here, you can see you get a square wave. This is a square wave. And basically, if we're looking into that, square wave just make up by the sine wave. Okay? That means different harmonic. They will be making up the square wave. You can see that. And now, what the basic definition for the bandwidth? Bandwidth equal what?
Upper frequency minus lower frequency?
What bandwidth equal?
Oh, -3.
Haha.
Is the difference between the upper cutoff point and the lower cutoff point.
Okay, basically you say the bandwidth means the difference between the higher and the lower, right? Frequency.
Right, Mr. Fan.
However, in general, bandwidth equal frequency maximum minus frequency minimum. That's general definition for the bandwidth. Okay? And now, what is the bandwidth for 1 kilohertz sine wave? What is the bandwidth for 1 kilohertz sine wave?
1 kilohertz. Isn't it 1 kilohertz?
Equal what? Nobody tell me equal what? What is the bandwidth of 1 kilohertz sine wave?
Isn't it 1,000 hertz?
Okay, you say 1,000.
Well,
500.
the upper would be 1,000, the lower would be 0. No?
So your answer will be 1,000 or 0.
1,000.
Who else? The
500.
What?
500.
Okay. Now, basic definition. Bandwidth equal maximum frequency minus the minimum frequency. Okay? So for 1 kilohertz, what is the maximum frequency?
1,000.
1,000. 1,000 hertz. Right?
Yes.
What is the minimum frequency?
0.
Zero.
Why you say 0?
Oh, it's 1,000.
Minus a
Also a 1,000.
So it's 0. Bandwidth is 0?
Right. The bandwidth is the difference between 1K minus 1K is 0.
Oh, so that means there's no band really. It's just one.
Right.
Yeah, okay.
Can you understand that?
I think so.
Yes.
Can you explain it again?
What I'm saying is the bandwidth of 1 kilohertz sideways is 0. Why 0? The thing is F maximum 1 kilohertz. F minimum will be 1 kilohertz. 1 minus 1 is 0. So that's why when you see the sideways on the oscilloscope, you cannot see two sideways. You can only see 1 kilohertz, that means only 1 kilohertz. If you want 2 kilohertz, you got only 2 kilohertz. You cannot get another one. Yes, right?
Yeah.
Okay, now, I already said, tell you, square wave, basic square wave will be made up by the sine waves, by different harmonic. Like the first one, they get a fundamental frequency. I given you, for example, 1 kilohertz sine wave. Third harmonic will be 3 kilohertz. Fifth harmonic 5K. Seventh harmonic 7 kilohertz, and so on. They keep going, so that's why they make it up a square wave. So, my question is, what is the bandwidth of 1 kilohertz square wave?
Zero.
Infinity?
What is the bandwidth of the 1 kilohertz square wave?
0.
Huh. That's what you interview they asking you. The thing is that only requirement understanding. You don't have to do any calculation, anything else. No formula.
1,000?
You say 1,000, 1K. Who else?
Any frequency you want.
Don't you need more information for that?
I think like 2 slides is a good description. I think it's 1 kilohertz.
Okay, now I can tell you. If they asking you what is the bandwidth for 1 kilohertz square wave, and now you must be asked them before you can answer. The thing is a square wave make up by too many sine wave with different harmonics. So you have to asking them to see what harmonic you want to count up to. That means they get too many. Okay, 1K fundamental, 3K third harmonic, 5K fifth harmonic, 7K, and so on. That's too many. We don't know how to do in calculation. Okay, so if I telling you, okay, just go up to 5 harmonic. Now, what is the bandwidth?
5,000.
4,000.
What? What number?
4,000.
Very
5,000.
good. Perfect. 4. Now, we do a little calculation. F maximum, you all go up to 5 harmonic, that means 5K, 5,000. That is the maximum, F maximum. F minimum is 1K. So you take 5 minus 1, you get 4 kilohertz. Does it make it clear for you guys?
Yes.
Wait, so 1,000 is the lowest. And
That's the base,
What?
that's the fundamental. That's F minimum. And now they
Okay.
want to count up to 5 harmonic, that means 5 kilohertz. That means you take 5 minus 1. So, any question? I said this is a knowledge, okay? Require you understanding.
Mr. Tai, if I understand you right, you're saying if it's the 1 kilohertz, the bandwidth of 1 kilohertz fundamental, which is the maximum, when it's maximum frequency minus the minimum frequency.
Yet, if you get to frequency, they give it to you.
Uh-huh.
But the question here, we're just asking for 1 kilohertz only.
Right. If it's 1 kilohertz, it's the max minus the minimum, so it's 0.
Right,
Correct?
exactly.
But then when you say the bandwidth of square wave, 1 kilohertz square wave, which is up to 5 kilohertz, you take 5 kilohertz and minus the 1 kilohertz.
Right.
Now, why do we have to minus 1 if
F
1,
maximum will be 5K.
right, that
F minimum,
minimum is 1K when they
right,
add,
1K.
okay,
So that's why you get 4.
okay, all right.
The reason is when you're working on like the filter, you can get upper lower. That means they different frequency. My question here just deal with a single 1 kilohertz or single square wave. Okay, now complex waveform. A complex waveform is any signal that is not a sine wave. You can get square wave, triangle wave, sawtooth wave, human voice, music, or digital data. Okay, so that is complex waveform. Any periodic signal that is not a pure sine wave can be considered to be built out of the following components. First thing, you get a DC component or average. Fundamental sine wave that has a frequency exactly the same as the frequency of the signal. Number 3, an infinite number of harmonics. Okay, harmonic is a frequency that is exactly multiple of the fundamental frequency. They get a note here. In the perfect square wave, there are infinite number of the frequency present. We only need to analyze up to 13 harmonics in order to get a decent reproduction of the square wave. So basically, if you have to deal with the square wave, they get too many harmonics of the sine wave. So they want you to count up to 13 harmonics only. Okay, that's good enough. Like last example, I given you 5 harmonics. But normally technician will be deal with 13 harmonic.
And each harmonic is just represents a rise of 1K in frequency.
Yeah, if they give a fundamental 1K, 13K.
Oh, got it. Okay.
Okay? Now, we're talking about again time domain and the frequency domain. You already know the time domain. That's oscilloscope. Okay? Now you get the square wave. 1K. Okay? Then you can get the square wave here. That's only one frequency. You can get another frequency. You understand the 1K, they can get too many different harmonic sine wave. However, if you display on the oscilloscope, the time domain, they display only 1 kilohertz square wave. Okay? In order to get the different harmonic of the square wave, the equipment you have to using will be spectrum analyzer. That means the frequency domain. You can say this is the frequency in kilohertz. On the other one will be the time t. Okay? So when you're looking on the spectrum analyzer, first thing you can get the signal sine wave for 1 kilohertz at the value 0.9 volt. That means they're telling you the signal at the frequency 1K, what is the value. Okay? Then the next will be second harmonic they're not using. You go to the third harmonic means 3K, and the voltage now 0.3, and they keep going. You see that? They can get the fundamental. Then the third harmonic, fifth harmonic, and seventh harmonic, and so on. So basically, spectrum analyzer will be a frequency domain. They can telling you at a certain frequency what is the value of the signal. But they are sine wave, but you cannot see sine wave. Sine wave only display on the oscilloscope, not frequency domain. So when you're looking to the two picture here, then you must be understand the second one. Okay? The first one you already know. That's just a square wave display on the oscilloscope. However, the same square wave, when they display on the spectrum analyzer, you can see. The difference is you cannot see any square wave, any sine wave. Only thing they given to you at 1 kilohertz. What the amplitude? 3, 5, 7, 9, so on. Just the value of the amplitude at a different frequency. In our program, okay, we get this equipment for you to working on a very basic lab, okay, to how to play with the spectrum analyzer. The thing is, this spectrum analyzer cost you much, okay? Scope you can buy $1,000. However, spectrum analyzer around 20,000. Okay, on the question here. Repeat now. We go. Same thing. They just display square wave in oscilloscope and square wave in the spectrum analyzer. Okay, so you can see that. Hopefully now you can understand what that means here. Fundamental. Okay, and that third harmonic and so on. We're not using even harmonic. Okay, just odd harmonic. If you're looking the same thing, square wave on the spectrum analyzer, you can see the display look like. Okay? Okay, now you can see this thing. Try to see you can understand. You get a square wave oscillator. What is the oscillator? You can go into the electronic store and you're asking for to buy oscillator.
The crystal.
Crystal, exactly. That means when you want to buy the oscillator, you must tell them what frequency you want. Very simple thing. You can say, okay, I want 10 kilohertz oscillator, 1 megahertz oscillator, whatever frequency. Okay? Only thing is when you connect the power to that oscillator, automatically square wave will be coming out with the frequency you bought it. 10K, you get 10 kilohertz coming out. However, the voltage will be only 0 volt to 5 volt square wave. You cannot get higher. That relates to the digital circuitry. They get only 0 and 1. 0 means 0 volt. 1 means 5 volt. So oscillator, they given you the frequency you want. However, the coming out only 2 level. Square wave, but not negative. 0 up to 5 volt only. Okay? And now you see 1 kilohertz square wave. So when the output of 1 kilohertz square wave here, okay, how many signal will be coming out?
1K.
How many? You get 1 kilohertz square wave.
1000.
One cycle.
I asking what frequency? How many
One
frequency
one
coming out?
K.
One frequency, 1K.
1K.
No. I already telling you. 1 kilohertz square wave make it up by too many frequency of a sine wave. That means you can get a first 1K, next will be
Third.
third harmonic 3K, and the next will be fifth harmonic, and so on. That's a square wave.
Okay.
Okay? We
Okay.
already explained to you. So the signal coming out here, they can be too many different frequency. Okay? And now I say, I want the signal only 3 kilohertz. Only coming out at the output here. I want only 3. If you connect directly to this point, you can get too many different frequency. 1K, 3K, 5K, 7K, so on. But if you want only 3K coming out, what can we do?
You can put a 4. Oh, no, never mind.
You need to put it up the filter,
Triple.
right?
You
This is
use
a
the bandpass
filter,
filter that only lets the 3K out.
right?
Oh,
That
okay.
means you need to add in, you design a band pass filter with only key 3 kilohertz. So any frequency lower than 3, they not allowed to go. Any frequency higher than 3, they not allowed to pass. So the coming out here only 3K. So now you understand the filter. Low pass, they pass any frequency from 0 up to cutoff frequency. High pass, they allow any signal from high frequency to cutoff frequency to pass. Any signal less than cutoff, they block it, stop. Okay? Band pass, you get upper frequency, lower frequency. Any signal with a frequency less than lower, stop. Higher than upper, stop. They allow only signal between the lower cutoff and the higher cutoff to pass through it. Okay?
Mr. Pham, so you're saying that the in between the 1K and the 3K, it's a unstable, noisy environment up until the third harmonic?
Now, I don't know much about that thing. Okay? But they ignore even harmonic. They not
Well
even,
then,
that's the
well
way
then,
they design.
what you're saying in between the 1K, the square wave can't even get to the shape of a square wave. It's an unstable wave. It doesn't even have a defined shape up until the third harmonic. It's not officially a square wave until the third harmonic. Or no, that's not correct.
You remember, 1 kilohertz square wave, they can get just the odd harmonic, 3K, 5K, 7K, so on. So they display in here telling you third harmonic will be part. They want 3K. Less than that, higher than that, they be blocked. That's a very good example. You understand how the signal coming out from square wave 1 kilohertz. How do we select only frequency you want? By using band pass filter. Okay, now electronic communication is everywhere. Watch a TV broadcast or listen to the radio, your telephone, your remote control, and more. Okay, electronic system. The system can be defined as a group of components that work together to complete a job or a task. A subsystem is just a part of the system. It helps to complete a task. A subsystem is often shown in the block diagram. Now, they given to you for simple radio. That is the transmitter. Okay, that means the radio station transmitted. And the other one is your radio. That is your receiver. Okay, that's a general. That is a transmitter, and that will be receiver. Okay, a microphone is a type of transducer. What is a transducer?
Converts one form of energy into another.
Right, converting one energy to the other. Okay, or we can say a sensor. It converting pressure variation in a sound wave into electrical energy. A transducer is any device that converts one form of energy into another. The transmitting antenna converting the amplified information signal into a new form of energy capable to traveling through the space. This new energy equal electronic magnetic energy or radio wave. Okay, so basically antenna here, they just converting, okay, one energy to the radio wave. Electronic energy consists of two fields, a voltage or electric field and a magnetic field. It travels through the space at the speed of light with about 3 times 10 power of 8 meter per second. Okay? This is, I recommend you have to keep reading over and over. So next time if they can ask you, what a microphone is what they doing. Okay? Transmitting antenna requirement. So they're talking about if you want to make antenna, then you need to understand radio transmitting antenna need to be at least 1/4 of the wavelength long. That means depending on the wavelength, you can build the antenna. Audio frequency are those we can hear. They are from 20 Hz to 20,000 Hz. And audio frequency that is in the middle of our hearing ran 1,000 Hz or 1 kilohertz. Okay? Let's calculate the wavelength of 1 kilohertz electromagnetic wave. So lambda equal V divided to F. That means 3 times 10 power 8 meter per second. Divide 1 kilohertz. You get your antenna long 300 kilometer. No way. You see that? The thing is the wavelength that the distance occupied by the wave on the air. And now if you occupy 300 kilo ohm per meter, there's no room for someone else to do something. They cannot do it. But that is the way to calculate the lambda. You take the speed of the light, divide to the frequency you want. Antenna need only be a 1/4 of this distance, or you will be get 75 kilometer long for your antenna. Increase frequency always decrease the wavelength. Decrease frequency will be increase the wavelength. We already know. Let's try change 1K to 10K. And after you doing calculate, antenna long will be 7.5 kilometer. If a frequency equals 150 megahertz, now your antenna long will be 0.5 meter. That only telling you one thing. At a very high frequency, so the antenna will be very short. That we're talking about the wavelength and the way how to get your antenna.
Question, Mr. Pham.
Yeah.
How happens that in the antenna the electrical pulses that the transceiver put in that antenna is transformed in an electromagnetic signal?
Right now they're talking about how you can build. If you want to build.
Sorry, again, please.
That means how you want to build your antenna.
Yeah. Okay, but there is a way that you can explain a little bit how that transformation happens in the antenna, that we have an electrical signal in a piece of trace, metallic trace, and then we have an electromagnetic pulse traveling through the space.
Yeah, that's around the antenna, but right now they just talking about in order to build the antenna. Then you have to know what your frequency.
Okay, thank you.
Second thing, you have to calculate your wavelength. Take your wavelength divide by 4. So they're telling you how long.
Yeah, no, I understand that point, but
That's okay.
I was trying to ask you how the transformation between electrons, flow of electrons in the antenna happens to an electromagnetic pulse that travels on the air.
Basically, when on the air, they not any problem. Only when they stack out of the antenna, or they can be reach the antenna.
Okay,
And
thank
that
you.
can be a problem. But transmitter, it's not. Okay? When you get about how they transmit it, then maybe more clear.
Okay.
Modulation. 150 megahertz signal may transmit just fine. But there one more problem. We cannot hear 150 megahertz. Why? It is too high in frequency. This is a solution. It is called a modulation. The thing is your voice. What's your frequency? 1 kilohertz. That is your voice. And you cannot build the signal for 1 kilohertz. You know, to build antenna for 1 kilohertz. No way. Okay? However, when they say, okay, you can bring it up to 150 megahertz, that will be transmitted, that will be fine. However, your ear not cannot hear any frequency too high. Okay? So that's what they get. The solution is called a modulation. When we modulate a wave, we place a low frequency information signal onto it. The low frequency signal is just along for the ride. It is in effect carrier on the top of the high frequency signal. The high frequency signal is therefore called a carrier signal. So basically what happened? Your voice only 1 kilohertz cannot transmit it over the air. The thing is that takes too long for the wavelength. Okay? In order to transmit it, they only transmit the signal with a very high frequency. With the wavelength will be shorted. So too many signal can transmit it over the air. However, when you're using the high frequency, they can transmit a high frequency. However, your ear cannot hear anything. Okay? So that's why they using what they call a modulation. Modulation, that means they're using the high frequency to carry your voice through the air. That is modulation.
Mr. Pham, I just wanted to make sure it, because cell phone antennas are small, that means that we use an antenna, we build the antenna for the carrier frequency, right?
Right, they must be carrier.
Okay, thanks.
Without carrier, you cannot transmit your voice. The thing is your voice is low frequency, standard 1 kilohertz, and that the wavelength will be too long. They cannot transmit it over the air. The thing is on the air, too many signals transmitted. If you occupy too much space in the air, so no one can transmit it. Okay, many mobile FM radio unit operate near 150 megahertz. At this frequency, wavelength lambda equal 2 meter and L minimum lambda divide 4. So the antenna will be 19.7 inches. Frequency above the range of hearing are called radio frequency. Any frequency over 20K is considered a radio of frequency. You cannot hear any signal at a frequency 20K or up. Okay, example 1. What is wavelength of 710 kilohertz AM broadcast signal? What is the minimum height of the antenna tower in feet if it is 1/4 of wavelength long? Can you do that for me? The first time I just go into the handout to get your idea, and later I will try to go into each problem to get more detail for you.
I got that circuit to work, Mr. Pham, if you want to see it.
So what is the wavelength of 710? Okay. The
Uh,
formula you know, right? Equal V divide F. V means the speed of the air. 3 times 10 power of 8 meter per second. Divide to
1.38
710.
feet.
Okay, let's see. Okay, if you're doing a calculation right, you can get wavelength 422.5 meter. And also, you can take the quarter of the wavelength. That means you can get 105.6 meter. And you can change it to how many feet. 105.6 times 3.28 feet per meter. So I let you download the PowerPoint. So now you can typing in your handout. That will be helping you to keep reading over. Not much, but very important thing to you. Okay. Number two. Lấy quarter wave lambda divided by 4. With antenna measure 108 inches. What is the approximate operating frequency? Now they add F. Who can get the answer for number two?
One 1.296 gigahertz? No, that's not right.
We say 27.3 megahertz. First thing lambda divide to 4. You get 2.74 meter. The purpose is you calculate the wavelength. After you get the wavelength, you using formula F equal V divided to wavelength. V means 3 times 10 power of 8 meter per second. And that answer will be 27.3 megahertz. If you're done, copy it, let me know. I can move on.
I mean, just a couple more seconds, Mr. Pham.
Yeah, go ahead. Keep going. When you're done, let me know. If you're reading any IF communication you cannot understand, I have to spend too much time to prepare in order for you guys able to follow it.
Okay.
Okay, let's see what next. Okay, there are 3 ways we can impress information onto a carrier. First one, we can change the voltage or the power of the wave is step with the information. This is what we call a amplitude modulation, AM. That means you can change the voltage. That's why AM. A means amplitude modulation. Second thing, we can alter the frequency of the wave with the information. This is called a frequency modulation, FM. Okay? AM means carrier will be change the amplitude of your voice, of the signal. FM means carrier will be change the frequency of your signal. And the last one, we can change the phase of the carrier wave. This is called phase modulation, PM. At least you must be understand when they talking about AM, FM, or PM. AM means carrier will be change the amplitude of your voice. FM, they change the frequency of your voice. And PM will be change the phase. Okay? A practical radio system. Every radio transmitter is assigned to operate on a specific carrier frequency. The job of the carrier oscillator is to generate this frequency. So that's why you can say you tuning to AM radio. They already get this different channel. Okay? 760 or whatever, they already separated frequency for each station. Okay? The purpose of an oscillator is to convert the DC from the power supply or into an AC signal. That is the purpose of oscillator. The output of carrier oscillator is nearly pure sine wave. The modulator has two inputs. First, the radio frequency sine wave from the carrier oscillator. And the second thing, the information signal means your voice. Okay? The output of the modulator is modulated carrier wave. That's just a new to everyone. So try to understand, okay? For the oscillator circuitry, they get one input from oscillator carrier. Another input is from your voice, called information signal. The output of the oscillator or modulator is modulated carrier wave. So when they're talking about modulated carrier wave, you have to know what kind of a signal. That's just a definition. Okay, checkpoint. I don't think you can answer. What is the purpose of oscillator circuit? I given you the answer.
Convert DC to AC.
The job of carrier oscillator is to converting the DC from power supply into an AC signal carrier frequency. That is the job of oscillator. That's a definition. Next time meeting I ask you, you're able to answer me, okay? Have to study. Number 2. How does an RF amplifier differ from AF amplifier? First thing you have to understand RF amplifier, that means radio frequency amplifier. AF amplifier means audio frequency amplifier. Okay, this is the definition. RF is a non-linear amplifier and AF is linear. Then now we need to understand what that means for non-linear amplifier or linear amplifier. Okay, first thing, audio amplifier is linear. Linear amplifier, that means you cannot change the gain of the amplifier. If you want to do it, then you have to go into the circuitry, change the value out of the resistor, okay, try to make a different gain, but not automatically change. That audio frequency amplifier. Linear. Non-linear linear, that means the amplifier, they can change the value. Without you can do anything. Okay? They can get the gain equal 2, then they can get the gain equal 3. Okay? Automatically they can adjust it. That will be non-linear amplifier. And what is the purpose of the modulator circuit?
To prepare the signal to go through. Oh,
The purpose of modulator circuit is combine the carrier oscillator and the information, or they call a message, or that basically just your voice, to produce a modulated carrier wave. Keep reading over until you can talk without looking into any paper. So basically, the signal for the radio, they transmit over the air. Okay, before they can reach your radio. So number 4, how many radio signals can be expected in the antenna circuit of the receiver? Receiver means your radio.
Infinite?
Infinite many?
Many. Very good. 1,000 signal. Too many. What does a radio receiver select one signal from 1,000? That means they're over the air, they get 1,000.
Resonance, LC circuit. Resonance LC circuit, cutoff frequency.
Uh-huh. Now you know resonance. Very good. LLC resonance circuit at a band pass filter. This filter is tuned in to the carrier frequency of the transmitted station. That means you tuning L and C to reach the resonance at the radio station you want. And number 7 will be
Hey, Mr. Pham, can you go up a little bit on 7?
go a little up.
Yes.
No way, I cannot.
Okay.
Sorry. I think that we run the we don't have any homework, okay? Anything on the Yeah. This time we really want to make sure you get an idea about the radio frequency.
Not everybody, Mr. Pham, but some of us still have to finish up our decibels.
Yep.
Yes.
I wanted to ask you something kind of related to this.
What?
I wanted to ask you something kind of related to the topic we're talking about. I wanted to see how does the fiberglass affect the signals? Like, why is everyone using fiberglass now?
I'm not quite following your question.
Okay. Yeah, I just, I was just wondering how does the fiberglass affect the signals? Because everyone's using fiberglass now.
Using what?
That's part of the circuit board.
Fiberglass what?
Glass is similar to a crystal.
Is you talking about the lab or what?
Like an oscillator that is made of fiberglass? What do
Yeah.
you mean by fiberglass? Oh.
Yeah, correct.
Consider anything that's glass is silica. So that's also referencing a crystal.
I'll just look it up online later. That's fine. Don't worry.
Yeah, maybe we're not up to that point.
Yeah, probably.
Right now, just the general information you have to get through it. Okay, number 7. What happened in detector circuitry? That means when the signal already go into your radio. It takes the incoming modulated wave carrier waveform and strip away the carrier frequency, leaving a copy of the original information signal. That means when they reach into radio, modulated wave, carrier wave, they have to remove the carrier frequency to get it back your voice. That is a detector. You done everything on the display?
No, I need another minute, please.
Make sure you have to spend time to read over and over and over in order to understand.
Okay, I'm good. Thank you.
Okay. Let's see what night. Okay, that practical radio system. One will be transmitter and another one will be receiver. Okay, on the first one, you can see you get a circuitry modulator. That is a circuit modulator. Okay. In this transmitter, very simple. To see that the modulator circuitry, they get you input, one coming from IF carrier oscillator, and another one where we get the void here, okay, and go to the voltage amplifier. Well, how come we need that amplifier? This is a microphone. What microphone will be using for?
Convert audio into electrical signals.
Very good. They converting from your voice, sound wave, into electrical wave. However, that signal will be really weak, so they need to make amplify, so they can get enough voltage to working with the other circuit. Okay, so you can say that only two input and a modulator inside, they can get the amplifier. What type of amplifier inside modulator? They can be linear or non-linear.
AF?
In modulator, they get an amplifier. However, the question is, that amplifier will be linear or non?
Linear?
No,
Oh, non-linear.
none. The thing is, that amplifier inside here, they can change the gain without you touch into that. Okay? Audio amplifier linear. You want to change the gain, you have to change the component. Okay? And the output of the modulator, they need to go to RF power amplifier. That means we want to increase the power of the signal before you can go to the antenna and transmit it. So you see the picture of the transmitter, very simple.
Now, did you say it is linear or non-linear?
Inside the modulator, you get an amplifier that must be non-linear.
So that's an RF amplifier?
Right. Anything here will be IF. Okay, now if you're looking into the receiver, that's for your radio. First thing is you get the antenna here. Receive antenna. That means how many signals transmit out here?
1,000.
1,000, too many. Okay? And now you can get the band pass filter, you adjust the capacitor, okay, inductor, whatever, in order to select the resonant frequency go here. Okay? and the signal is not good enough, so that's why they need amplifier. Okay, so after they amplify, they have to go to the detector, the modulator. The reason is when the signal coming into here, okay, this signal will be include your voice and the carrier, and also you can get a DC component. So the purpose of the detector here is remove the carrier and any DC if they have it to get only your voice. That is the detector want to do. They call it the modulator. Then they go amplify, then go to speaker. That's how your radio working.
So the knob that we tune in the stations like a variable capacitor?
Right, exactly. So you can adjust it. When you tuning on your radio, you changing capacitor to select the resonance. The thing is in the RF, you have to understand what your modulator try to do. You don't care what inside. Okay, no way. Or the detector or the modulator. What they supposed to do. Their job. Okay? But we don't care what inside. Okay. Making an AM signal. Okay, after this page, we can stop. And we'll be continuing tomorrow. Make sure you get the time to read it over and over. Okay, now you can see in here, modulator amplifier here. RF carrier oscillator. That means high frequency go this way. And intelligent input means your voice going in. And this is the amplify non-linear. Okay? They can change the amplitude of the signal. And the coming out, we call amplitude modulated output. You can see how simple, right? So, the first step in any transmitter is oscillator. Okay? Any transmitter. The first input must be oscillator. The RF carrier wave contain no information until it is modulated. That means the signal output of the oscillator have nothing to do with your voice. Okay? The only thing happen after they modulate it. Okay? In order for amplitude to be changed, the voltage or the power gain of a subsequent state must be changing. So they will be changing the voltage here. Okay? AM generator had a special amplitude with a variable voltage gain called modulator. The amplify with a constant gain equal a linear amplify. Okay? That means the gain cannot be changed. If you want it, you have to working with the hardware to make it change, not automatic. The variable gain amplifier is a non-linear amplifier. So they automatically changing the gain. A non-linear amplifier is always required to generate AM signal. This handout I summarize from too many different books, okay, in order to combine to make it more sense for the people reading can understand. So you want to understand about radio frequency. The better way is try to keep reading over and over. When they're talking about oscillator or modulator, what is the information signal? What is a linear amplifier or non-linear amplifier? What the name of the signal when they get out? Modulator. Okay? That's a new for everyone. So can try to read over and over. Any question?
Mr. Pham, I have that circuit running if you'd like to see it.
Okay, I can stop share here. You can share.
Hey, Mr. Pham, while he's doing that, on digital review number 4, problem 5 should be in watts, not volts. On your Excel, you got it in volts.
Okay. Yeah. That's what he tried to simulate it very good. You can see the signal out of the modulator.
That's about what, 50%?
That look like 100% modulated or not. When you get into next time, you're able to do in calculation. But that is a signal coming out of the modulator. That's a perfect. That you're using the pitch 5, right?
Isn't it Falstad?
We've done it before on P-Spice, Mr. Pham.
No,
That's Falstad.
yeah, no. Can you send me that file?
Yes, I can. That's Falstad. That's our breadboard project from about probably 2.5 years ago.
Okay.
Yes, I'll send you the link right now.
Okay, that's a very good thing. Okay. And that will be, I can working on that and try to see we can get few more different simulation program for you guys exercise. Okay.
Can I show you my new toy?
Yeah. that's a very good toy for anyone want to working in the electronic. Okay, so we'll see you tomorrow.
Hey, Mr. Pham, don't forget on digital review 4, problem number 5 has to be changed to watts, not volts on your
You
on your
mean
Excel.
you mean AC review number 4?
No, decibel review 4.
Hold on, Mr. Pham. I'll send it to you right now. All you have to do is go to Falstad.com. I'll provide the link for you. Then I'm going to paste the circuit code as part of a message to you here on Zoom. And all you have to do is copy it from Zoom, put it in Notepad, and then when you're at Falstad.com, you import the code, and it will automatically load that circuit for you. All right, stand by.
Okay. Oh no, get that some student asking me about the lab problem. I told him, okay, we'll be talking today, but I don't know who.
Yeah, so all you have to do, really do on mine, Mr. Pham, is just make a change on decibel review 4, and where it says volts for number 5, it should say watts.
Okay, I will look into that decibel number 4. Right?
Decibel number 4, problem 5.
Here comes the link, Mr. Pham.
Okay.
All right,
you.
just go ahead and go load that up into your website real quick so you can be on the website.
Okay.
And I can walk you through it real quick.
No, that's okay.
All right, here, let me send the code over to you. All right, that's the code. All you have to do is copy that and import it.
Okay.
You'll have to go to File and Import as a text file.
Okay.
And then it will automatically load all the circuits.
Okay.
On the scope, do a right click and you'll have properties for the scope, and you can do adjustments for the Fourier, the current, voltage, spectrum, and then the generators are self-explanatory. Just click on them. They're very simplified. And then all the circuit components, just click on the line, the component, doesn't matter, and it's all self-explanatory.
Okay.
You're welcome. Enjoy your evening.
Thank you. Okay. Good night, everyone.
Good night, Mr. Pham.